satellite imagery and they realize, oh my God, that's the caldera of a volcano, like this Yellowstone thing. We thought it was just this crazy place with hot springs. Like, no, that's a supervolcano that is a continent killer.
Below the picturesque surface of Yellowstone National Park lies a troubling development that has recently caught the attention of scientists. Renowned podcaster Joe Rogan has brought to light a significant change occurring in the park, a massive dome-shaped uplift that is steadily growing. This raises the question, is Yellowstone's dormant giant starting to stir? And if so, what might the repercussions entail for us? Let's delve into the details and examine the importance of this expanding dome-shaped uplift. Yellowstone National Park, nestled in the American West, is not only a testament to nature's beauty, but also harbors a potentially catastrophic geological phenomenon, the Yellowstone supervolcano. This colossal force of nature holds the capacity to unleash unimaginable devastation upon its awakening. The volcanic history of Yellowstone is as intriguing as it is unsettling. The region has witnessed monumental eruptions of unfathomable proportions. According to Joe Rogan, the recent growth of the immense dome-shaped uplift is causing concern among scientists. The precedent for Yellowstone's extraordinary volcanic activity was set by the Huckleberry Ridge eruption. This cataclysmic event, one of the largest in recent Earth history, gave rise to the initial Yellowstone caldera, a massive volcanic crater that remains a defining feature of the park today. Subsequent significant eruptions, such as the Mesa Falls eruption around 1.3 million years ago and the Lava Creek eruption approximately 640,000 years ago, further shaped Yellowstone's intricate volcanic landscape, molding the region's topography over time. The Mesa Falls eruption, although smaller in scale compared to the Huckleberry Ridge event, was still immensely significant. It resulted in widespread ashfall that blanketed large swathes of the present-day United States, altering the landscape and affecting the environment. Interestingly, the opening created by this eruption partially overlapped with the earlier Huckleberry Ridge opening, highlighting the ongoing volcanic activity beneath Yellowstone. The most recent eruption of the three, the Lava Creek eruption, led to the formation of the current Yellowstone caldera, the park's largest and most prominent volcanic feature. This eruption was so colossal that it expelled a vast amount of volcanic material, spreading ash as far as the Mississippi River and the Gulf of Mexico. Subsequently, it formed an opening that stretches nearly the entire width of the park. These eruptions exerted significant influence on the global climate, impacting weather patterns and resulting in cooler temperatures worldwide. The ash and gases released into the atmosphere during these events likely contributed to volcanic winters, where sunlight was partially obstructed, leading to reduced global temperatures. Such climatic shifts could have affected ecosystems and wildlife, altering species distribution and potentially exerting evolutionary pressures on plants and animals. Beyond their climatic ramifications, these eruptions played a pivotal role in shaping the distinct geothermal features that characterize Yellowstone National Park. The repeated filling and emptying of the park's magma chamber fueled the creation of its renowned geysers, hot springs, and other hydrothermal marvels. The warmth that fuels these remarkable features emanates from the still-active magma chamber beneath Yellowstone National Park, directly tracing back to the volcanic eruptions that sculpted the park's landscape millions of years ago. Today, the remnants of these ancient volcanic eruptions offer invaluable insights into volcanic processes and the Earth's geological history. The layers of volcanic rock and ash deposited by these eruptions serve as a geological archive, enabling scientists to reconstruct the timeline of volcanic activity in the region. This archive not only sheds light on Yellowstone's past, but also aids in predicting future volcanic behavior and evaluating the potential hazards associated with the park's supervolcano. Therefore, the study of these eruptions and their aftermath remains a critical component of geological research in Yellowstone. At the core of the present volcanic activity lie the Sour Creek Dome and the Mallard Lake Dome. These formations deviate from typical volcanic structures, resembling enormous bulges on the Earth's surface caused by the upward pressure of magma replenishing the magma chamber beneath. To grasp the significance of these domes, envision a colossal subterranean balloon gradually filling with magma. As this balloon expands, it exerts upward pressure on the ground above, forming a dome shape. Essentially, this is the process unfolding beneath the Sour Creek and Mallard Lake areas. These domes are substantial, spanning several kilometers in width and rising hundreds of meters above the chamber floor. Recently, scientists have observed peculiar developments in these formations. The emergence of these reawakening domes serves as a stark reminder that the volcanic system beneath Yellowstone is anything but dormant. Rather, it signals the presence of a restless giant lurking beneath the park's tranquil lakes and awe-inspiring geysers, patiently waiting its moment. The recent announcement regarding the expansion of the dome-shaped Uplift serves as a poignant illustration of the dynamic and potentially hazardous nature of this supervolcano. Yellowstone's supervolcano, characterized by a history of catastrophic eruptions that have dramatically altered the landscape and influenced global climate, remains an ever-active force. The formation of landmarks like the Yellowstone caldera and resurgent domes, such as the Sour Creek Dome and the Mallard Lake Dome, underscores the continuous volcanic activity beneath the park. Understanding these geological formations is paramount, as they provide invaluable insights into the behavior of the supervolcano and the associated risks. Recent observations and warnings have heightened scrutiny on Yellowstone National Park, owing to a series of unsettling indicators pointing toward heightened geological activity. Chief among these is the substantial enlargement of a dome-shaped uplift within the park, a profound shift in its foundational structure, hinting at stirring forces beneath Yellowstone's surface. Adding to the apprehension are the enigmatic fluctuations in Yellowstone Lake's water levels. Scientists have noted irregularities in the lake's stability, manifesting as a tilting motion akin to a seesaw, suggesting potent and dynamic forces at play below. This tilting phenomenon serves as a warning sign of alterations in the underlying volcanic system. Moreover, the emergence of extensive fissures in the terrain has sparked widespread speculation and concern. These fissures potentially signify movement of magma beneath the park's surface, underscoring the tangible and imminent danger posed by Yellowstone's ongoing volcanic activity. The recent observations in Yellowstone, spanning from the expanding dome-shaped uplift to the fluctuations in water levels and the emergence of new fissures, serve as unmistakable signs of heightened volcanic activity. These indications have played a pivotal role in raising public awareness regarding the potential hazards associated with Yellowstone. Delving into the scientific explanation behind this surge in activity begs the question: why is it occurring now? Yellowstone National Park stands as a living laboratory, offering a vivid portrayal of the Earth's inner workings. At the heart of Yellowstone's geological intrigue lie the resurgent domes, notably the Sour Creek Dome and the Mallard Lake Dome. The significance of these domes transcends mere physical presence. They serve as vital barometers of the restless nature of the volcanic system beneath Yellowstone. The movements and expansion of these domes furnish crucial insights into the behavior of the magma chamber and the likelihood of future volcanic events. Effectively monitoring such a dynamic and intricate system necessitates cutting-edge technology, and scientists have made substantial advancements in this realm. Modern techniques such as the Global Positioning System, GPS, and Interferometric Synthetic Aperture Radar, INSAR, stand at the vanguard of these endeavors. GPS enables precise measurement of ground movements, enabling scientists to track even the slightest shifts that may signify volcanic activity. Complementing this, INSAR utilizes radar images from satellites to chart ground deformation across extensive regions. These technologies have revolutionized our capacity to monitor volcanic activity, furnishing detailed and continuous data that was previously beyond reach. Recent scientific revelations underscore the significance of this sophisticated monitoring infrastructure. The discovery of the expanding size of the dome-shaped uplift serves as a compelling example of the fruits yielded by advanced monitoring techniques. This notable alteration suggests movement of magma beneath the surface, potentially indicating an uptick in volcanic activity. Likewise, the sudden appearance of the Hidden Falls fissure, a substantial crack that seemingly emerged overnight, has captivated both scientists and the public. These discoveries underscore the dynamic nature of Yellowstone's geology and underscore the necessity for ongoing vigilance. The ramifications of these revelations are immense. Advancements in monitoring technology have granted us unprecedented insights into these processes, empowering scientists to monitor the park's volcanic activity with remarkable precision. But why do scientists harbor such deep concerns about a Yellowstone eruption? The potential eruption of the Yellowstone supervolcano is a scenario fraught with catastrophic consequences, both for the immediate surroundings and potentially for the entire planet. One of the most immediate consequences of such an eruption would be the widespread dispersion of volcanic ash. This ash, resembling fine abrasive sand, would blanket landscapes, suffocating everything in its path. This fallout could disrupt transportation networks, burying roads, railways and airports, thus halting travel. Yet, the ramifications of ash extend far beyond mere inconvenience. The accumulated weight of ash could induce building collapses, disrupt power supplies, and inflict significant structural damage. Moreover, this ash, laden with sharp particles, poses a severe respiratory hazard capable of causing severe health issues if inhaled by humans or animals. The environmental devastation would be profound. Ash and volcanic gases could contaminate water sources, rendering them unfit for consumption and damaging aquatic ecosystems. The sulfur dioxide gas emitted during the eruption could combine with atmospheric water vapor, precipitating as acid rain upon descent back to Earth. The consequences of this acid rain would be devastating for ecosystems, as it would lead to the acidification of lakes and rivers, harm plant life, and corrode built structures. In addition to its environmental impact, a Yellowstone eruption could trigger a volcanic winter. The vast quantities of ash and gases expelled into the atmosphere would form a dense cloud, blocking sunlight and causing a significant decrease in global temperatures. This abrupt cooling could have severe repercussions for agriculture, resulting in widespread crop failures and food shortages. In a world heavily dependent on stable agricultural yields, this could precipitate a global food crisis, with shortages driving up prices and potentially leading to famine in more vulnerable regions. The societal repercussions of such an eruption would be extensive. Infrastructure damage caused by ash fallout and seismic activity could disrupt essential services, ranging from healthcare to the supply of electricity and water. The health risks posed by ash and volcanic gases could strain medical services, with respiratory issues and other health problems becoming more prevalent. Regarding Joe Rogan's perspective on the recent incident in Yellowstone, Joe Rogan, a well-known commentator and podcaster, has a talent for delving into intricate topics and bringing them to the forefront of public discussion. His discussions on the Yellowstone supervolcano are no exception. Rogan has issued stern warnings regarding the latent dangers concealed beneath the tranquil scenery of Yellowstone National Park, captivating his extensive audience and elevating the discourse surrounding this geological behemoth. He underscored the immense power of the supervolcano and the profound impact its eruption could entail, both locally and potentially on a global scale. Leveraging his platform, Rogan effectively portrayed the formidable might of the supervolcano, drawing upon a wealth of scientific research to underscore the gravity of the situation. A notable aspect of Rogan's commentary is its alignment with scientific findings. Despite not being a scientist himself, Rogan frequently draws upon the latest research and expert opinions to enrich his discussions. This approach has enabled him to bridge the gap between the scientific community and the general public, translating complex geological concepts into accessible terms that resonate with his audience. Rogan's discussions regarding the recent disquieting signs observed at Yellowstone, such as the expanding size of the dome-shaped uplift and the emergence of fissures, echo the concerns voiced by scientists. However, how exactly do scientists discern the potential for eruption in this volcano? Monitoring the Yellowstone supervolcano necessitates a multifaceted network of surveillance efforts essential for deciphering the intricacies of this colossal volcanic system. Scientists and researchers are continuously engaged in vigilant observation, employing a variety of advanced technologies to monitor any fluctuations that may signify changes in volcanic activity. This meticulous work forms the bedrock of understanding the supervolcano's behavior, furnishing invaluable data that benefit both the scientific community and the general public. At the core of these monitoring endeavors lie state-of-the-art tools such as GPS and INSAR. These instruments go beyond mere observation. They play a fundamental role in disaster preparedness. By comprehending the intricate mechanisms of the supervolcano, researchers can devise potential strategies to mitigate the impacts of a potential eruption. This research focuses on predicting the timing of an eruption and understanding the progression of such an event, as well as identifying the most effective methods to safeguard lives and infrastructure. For instance, the examination of past eruptions and the behavior of resurgent domes within the caldera furnishes insights into the supervolcano's eruptive history and potential future activity. This knowledge is instrumental in formulating evacuation plans, designing resilient infrastructure capable of withstanding volcanic events, and implementing early warning systems to promptly alert the public. Furthermore, the ongoing research contributes significantly to the broader field of volcanology, enriching our comprehension of volcanic processes and their implications for the environment and human society. This reservoir of knowledge is essential for guiding policy decisions, crafting emergency response strategies, and launching public education campaigns aimed at enhancing awareness and readiness among vulnerable communities. The monitoring and research initiatives centered on the Yellowstone supervolcano form integral parts of a comprehensive strategy designed to safeguard lives and minimize the potential devastation caused by volcanic events. Through sustained observation, meticulous scientific inquiry, and the formulation of preparedness plans, we can better prepare ourselves to confront the challenges posed by one of nature's most formidable forces. Yellowstone National Park isn't merely the domain of the foreboding supervolcano lurking beneath its surface. It hosts a plethora of natural wonders, each more captivating than the last, offering a showcase of Earth's dynamic processes. From its geothermal marvels to its diverse biodiversity, Yellowstone provides a distinctive insight into the intricacies and splendor of the natural world. Situated atop one of the world's largest active volcanic systems, Yellowstone serves as a geological hotspot, fueling an unparalleled array of geothermal features found nowhere else on Earth. The park boasts an impressive array of over 10,000 hydrothermal sites, including more than 500 geysers. Among them, Old Faithful stands out as the most renowned, showcasing the park's turbulent subterranean activity by propelling scalding water up to 180 feet into the sky at regular intervals. However, Old Faithful is merely a glimpse into the park's riches. Its landscape is adorned with vibrant hot springs, bubbling mud pots, and hissing fumaroles, each contributing to the otherworldly allure of this volcanic paradise. The Grand Prismatic Spring, famed for its mesmerizing hues spanning from azure to ochre, reigns as the largest hot spring in the United States, a visual spectacle adorned with microbial mats along its perimeter. Yet, the park's wonders extend beyond its hydrothermal and geological marvels. The Grand Canyon of the Yellowstone, another awe-inspiring feature, narrates the park's tumultuous geological saga. Carved by the Yellowstone River over millennia, This canyon stretches roughly 24 miles in length, plunges up to 1,200 feet deep, and widens to over 4,000 feet in some areas. Its majestic walls boast a kaleidoscope of colors, courtesy of hydrothermal alterations to the rhyolite rock. The lower and upper Yellowstone Falls amplify the canyon's grandeur, cascading into the Yellowstone River and further sculpting the landscape with their majestic waterfalls. Beyond its geothermal and geological splendors, Yellowstone serves as a sanctuary for a diverse array of wildlife, rendering it one of the last untouched natural ecosystems in the northern temperate zone. Large herds of free-roaming bison, often regarded as a symbol of the American West, roam its expanses. Visitors may also encounter elk, grizzly bears, wolves, and bald eagles, each playing a vital role in maintaining the park's delicate ecological equilibrium. This diverse array of wildlife provides invaluable insights into conservation efforts, illustrating the intricate interplay between species and the complexities of natural habitats. Complementing the park's rich fauna is its diverse flora, comprising over 1,700 species of trees, shrubs, and wildflowers that adorn the landscape with a tapestry of greens, yellows, and purples. The sprawling expanses of lodgepole pine forests intertwined with aspen, spruce, and fir create a striking contrast to the park's geothermal regions. These forests not only serve as habitats for wildlife, but also play a pivotal role in the park's ecological processes, including the fire regeneration cycles that shape its terrain. Natural forest fires constitute a crucial element of Yellowstone's ecology, clearing out aged vegetation and paving the way for new growth. The 1988 fires, among the largest in the park's history, initially appeared as a catastrophe. However, the aftermath revealed nature's resilience and adaptability, with fresh growth flourishing in the charred areas, showcasing the role of fire in ecological succession and forest rejuvenation. Volcanic eruptions stand as some of the most potent natural phenomena on Earth, capable of reshaping landscapes, influencing global climates, and profoundly impacting both human and ecological systems. Throughout history, numerous eruptions worldwide have underscored the immense force and widespread repercussions of volcanic activity. But have there been concrete examples of volcanic eruptions and their devastating effects in real life? Let's delve into one such instance. The eruption of Mount Tambora in 1815 remains one of the most formidable eruptions documented in history. Its magnitude was so immense that it expelled approximately 100 cubic kilometers of magma, ash, and volcanic gases into the atmosphere, precipitating a global climatic anomaly famously known as the Year Without a Summer. The eruption of Mount Tambora in 1815 precipitated the Year Without a Summer, yielding profound socio-economic repercussions that reverberated worldwide. The ash and sulfur dioxide propelled into the stratosphere deflected sunlight away from the Earth, instigating abnormal weather patterns that persisted for years. Across Europe, the summer of 1816 was characterized by relentless rainfall, triggering catastrophic floods, decimating crops, and precipitating one of the severest famines of the 19th century. In North America, particularly in the northeastern United States and eastern Canada, snowfall in June and July frosts ravaged harvests, exacerbating food shortages. The ramifications of the eruption transcended the northern hemisphere. In tropical regions, the eruption disrupted the monsoon cycle, leading to irregular rainfall patterns that contributed to cholera outbreaks in India and famine in China. The global temperature anomalies induced by the eruption also disrupted ecosystems, prompting species migration to new habitats and disrupting natural predator-prey dynamics. Culturally, the drastic climate fluctuations inspired significant artistic and literary works. For instance, the bleak, frigid summer of 1816 is believed to have influenced Mary Shelley's creation of Frankenstein and Lord Byron's Darkness, both of which encapsulate the era's despondency and gloom. Furthermore, The Tambora eruption serves as a pivotal case study for comprehending the potential ramifications of volcanic-induced climate change. It furnishes invaluable insights into the immediate climatic repercussions of large-scale volcanic eruptions, aiding scientists in refining models that forecast the Earth's climate response to aerosol injections into the atmosphere, whether stemming from volcanic activity or theoretical geoengineering endeavors. The 1883 eruption of Krakatoa wrought immediate catastrophic effects and left an enduring mark on the world in numerous unforeseen ways. The eruption's sheer force equaled 200 megatons of TNT, approximately 13,000 times the nuclear yield of the bomb dropped on Hiroshima. The explosion's sound was so deafening that it registered as the farthest traveling sound in recorded history, audible as far as the island of Rodriguez near Mauritius, spanning about 4,800 kilometers away. The tsunamis unleashed by the eruption were equally unprecedented, with waves towering up to 40 meters high, annihilating coastal settlements and towns. These oceanic surges traversed the Indian Ocean, affecting shores as distant as South Africa. The human toll was staggering, with the majority of casualties stemming from these tsunamis. Furthermore, the atmospheric ramifications of the Krakatoa eruption were substantial and enduring. The ash and sulfur dioxide propelled into the stratosphere dispersed globally, forming a shroud that dimmed sunlight and engendered vibrant red and orange sunsets, famously depicted in Edvard Munch's painting, The Scream. This worldwide atmospheric phenomenon, dubbed volcanic winter, ushered in lower temperatures across the globe, estimated to have decreased by 1.2 degrees Celsius. The subsequent year, 1884, witnessed unseasonably cold weather, crop failures, and food shortages in numerous regions, underscoring the extensive climatic repercussions of significant volcanic eruptions. The Krakatoa eruption also represented a pivotal juncture in the realms of volcanology and atmospheric sciences. It stood as one of the earliest major eruptions subjected to systematic scientific inquiry, culminating in the establishment of the Volcanological Survey of Indonesia. Meticulous documentation of the global dispersion of ash and atmospheric phenomena yielded invaluable data that significantly contributed to the advancement of modern climatology. The eruption underscored the indispensability of global telecommunication networks, being among the earliest worldwide news events swiftly disseminated across telegraph networks, spotlighting the interconnectedness of the world in the face of natural calamities. The 1980 eruption of Mount St. Helens unfolded as a multifaceted catastrophe that transcended the immediate explosive event. Following the eruption, a colossal pyroclastic flow, an expeditious deluge of scorching ash, volcanic gases and debris, engulfed and razed everything in its path for miles. This flow was accompanied by volcanic mudflows that inundated river valleys, causing extensive damage to bridges, roads and structures, complicating rescue and recovery endeavors. In addition to the human tragedy and infrastructural devastation, the ecological ramifications of the eruption were profound. Roughly 230 square miles of forest lay devastated, morphing lush woodlands into desolate expanses. The intense heat from the eruption and ensuing pyroclastic flows sterilized the soil, initially rendering the area seemingly devoid of life. However, this devastation set the stage for an extensive natural experiment in ecological succession. In the ensuing years, scientists meticulously monitored the gradual resurgence of plant and animal life within the blast zone, furnishing invaluable insights into the processes by which ecosystems rebound from catastrophic upheavals. The eruption also spurred significant progress in volcanic monitoring and emergency preparedness. Prior to the 1980 eruption, Mount St. Helens had lain dormant for 123 years, underscoring the imperative for enhanced predictive capabilities. Consequently, the United States Geological Survey heightened its surveillance of the nation's volcanoes, particularly those in the Cascade Range, deploying novel technologies and methodologies to promptly identify signs of volcanic unrest. A paramount takeaway from the Mount St. Helens eruption was the criticality of heeding warning signals. In the months leading up to the eruption, the mountain displayed myriad precursors, including earthquakes, steam explosions, and the emergence of a substantial bulge on its northern flank. These indicators prompted authorities to designate a red zone encircling the volcano, a decision undoubtedly instrumental in saving lives, despite the challenges encountered in executing evacuations and enforcing access restrictions to the area. The Mount St. Helens eruption stands as a watershed moment in the realms of volcanology and disaster management. It underscored the capricious nature of volcanic eruptions and underscored the necessity for vigilance and preparedness in volcanic regions. The event's thorough documentation and the wealth of scientific data amassed continue to inform volcanic hazard evaluations and emergency response strategies, both domestically in the United States and globally, ensuring that the insights gleaned from Mount St. Helens remain pertinent in the realm of natural disaster mitigation. Despite its relatively modest volcanic output, the 2010 eruption of Eyjafjallajökull in Iceland wielded a disproportionate impact on human activities, chiefly owing to the extensive air travel disruption it instigated across Europe. The ash cloud engendered by the eruption precipitated the most extensive air traffic shutdown since World War II, affecting millions of travelers and engendering billions of dollars in economic losses. This event underscored the potential for even minor eruptions to exert significant societal repercussions in our interconnected world. The eruption of Mount Pinatubo in 1991 stands as the second largest terrestrial eruption of the 20th century. It unleashed a colossal ash column and expelled a substantial volume of sulfur dioxide into the stratosphere, resulting in the formation of a global sulfuric acid haze. This phenomenon led to a discernible drop in global temperatures by approximately 0.5 degrees Celsius in the ensuing years. Tragically, the eruption resulted in numerous fatalities, primarily attributed to the collapse of roofs under the weight of accumulated wet ash, and left thousands displaced from their homes. The eruption of Mount Pinatubo represents a pivotal moment in the fields of volcanology and disaster preparedness, owing to both its magnitude and the extensive measures taken to alleviate its repercussions. Prior to the eruption, an unprecedented evacuation campaign was initiated. Collaboration between scientists from the Philippine Institute of Volcanology and Seismology and the United States Geological Survey enabled the identification of warning signals such as seismic activity and gas emissions, indicating an imminent eruption. This joint effort facilitated the timely evacuation of tens of thousands of individuals from the vicinity of Pinatubo, undoubtedly saving numerous lives. In addition to the immediate human and infrastructural toll, the eruption engendered significant environmental ramifications. The widespread ash fallout affected extensive areas, impairing agricultural productivity and polluting water sources, exacerbating the humanitarian crisis. Moreover, the eruption resulted in a substantial crater at Mount Pinatubo's summit, fundamentally reshaping the mountain's landscape. One of the enduring legacies of Pinatubo's eruption was its impact on the Earth's atmosphere. The sulfur dioxide discharged into the stratosphere reacted with water vapor, generating a sulfuric acid mist that dispersed globally, forming a veil that reflected sunlight and cooled the Earth's surface. This atmospheric occurrence served as a tangible case study for scientists investigating the potential ramifications of aerosols on climate, furnishing invaluable insights to the field of climatology. Moreover, the eruption spurred advancements in the monitoring and forecasting of volcanic activity worldwide. The effective prediction and evacuation efforts underscored the significance of scientific surveillance and international cooperation in mitigating the human impact of volcanic eruptions. Subsequently, there was an uptick in investment in volcanic research and monitoring, which included the implementation of more sophisticated early warning systems and the adoption of novel technologies for detecting indications of volcanic unrest. These instances highlight the multifaceted consequences of volcanic eruptions, ranging from localized devastation and loss of life to global climatic shifts. Each event serves as a testament to the Earth's dynamic nature and emphasizes the necessity for continuous research, monitoring, and preparedness to mitigate the hazards associated with volcanic activity. The examination of past eruptions, coupled with the ongoing surveillance of active volcanoes, plays a pivotal role in forecasting future eruptions and executing effective disaster response strategies to safeguard communities and ecosystems in volcanic regions. Regarding Yellowstone's future, whether the enlargement of the dome-shaped uplift signifies a natural occurrence or a more perilous development remains uncertain. As we have delved into the depths of Yellowstone's volcanic core, it becomes apparent that vigilance, research, and preparedness are our foremost defenses against the capricious might of nature. Stay informed, remain curious, and participate in the dialogue as we persist in unraveling the enigmas of Yellowstone's dormant behemoth.